Hello. In this video, we are going to solve the system of linear equation. Prior to that, you just remember that in previous videos we have tried to understand how what is the meaning of matrix multiplication, in which we have seen that the matrix multiplication can be seen as the linear combination of rows of the matrix which is on the right hand side of the multiplication, and you can see it again as the linear combination of columns of the matrix which is appearing on the left hand side of the matrix multiplication. So first of all, we are trying to tell you what is the general form of system of linear equation, and what we are going to do in this particular uh, part of notes. So any general system of linear equation has a number of equations with a number of variables. So in this particular example, we have n number of variables and m equations. Uh, so it is a11 x1 plus a12 x2 plus a1n x1 is equals to b1. So each value a11, a12, a1n, b1, all of them belongs to real numbers, and x1, x2, xn are the variables. So if we convert it into a matrix form, we have seen in all the previous lectures that it can be written as ax is equals to b. So whereas ax is a variable vector, a is a coefficient matrix, and b is a constant vector. So matrix A is basically containing a11, a12, a1n up to a1n in the first row, then a21, a22 up to a2n in the second row, and so on. B vector B contains b1, b2, bm. It's a column vector. It's containing that, and x is again a column vector of x1, x2, xn. Now, since few things we know already about the matrix equation, if you have an ax is equals to b matrix equation and a is a square matrix, then possibly invertible matrix, then you can take the inverse. So if we pre-multiply the equation on the both sides by a inverse, then you get that x is equals to a inverse of b. So it means if we are trying to solve a system of linear equations, we are also going to work with the inverse. So in this part, we are going to focus on inverse as well as on the solving of system of linear equations. So essentially, both of them are similar problems. Okay, so let us the second subsection of this particular lecture is about the linear combination of columns and rows, which we have already done. So I'm skipping that. You can actually do it again so as to understand the things in more uh, in a better way, basically. So let us go and skip this part. Now coming to the Gauss elimination. Now, Gauss elimination requires a simple idea that look at this particular set of equations that we are trying to solve, um, which we can write it in this particular form. So, like the 2, 4, 5 are the multiples of x1, then 3 minus 2, 5 times x2, and uh, 5 minus 7 minus 3 times x3 is equals to 182. So this is again giving you the idea that ax, so if we combine these three columns, this column, this column, this column, we get a coefficient matrix, and this is the variable vector and this is constant vector. So looking or comparing the equation 1 and equation 2's left hand side of the equality, we can understand that ax is nothing but the linear combination of columns. So whenever we will say ax, you should understand that I'm talking about linear combination of columns of a, right? So if we talk about Gauss elimination, and we are doing it on rows. So we are doing it on rows of A. When we are doing it on rows of A, we have to remember that we are not only doing on the coefficient matrix, we are also doing the same operation on the constant vector, right? Since we are doing it on the constant vector as well as the coefficient vector, instead of doing it only on the means one time on the coefficient vector and one time on the uh, constant vector, coefficient vector and coefficient matrix and constant vector, so what we can do, we can actually combine them and make a augmented matrix. Make an augmented matrix, which is nothing but this one, right? So if we do the Gauss elimination with this particular augment in this augmented matrix, our complete process is done in one go. Let us try to see an example of the Gauss elimination in matrix. So as of now, we are talking a simple example. We are taking a simple example that has a unique solution. So let us talk that. So let us suppose that these three equations are there, which has the augmented matrix corresponding to this particular one. Now to remove this minus one, or doing some operation, some row operation, so that this minus one can be converted to 0, could be this one, that we add equation 1 to equation 2, and that will remove the coefficient of x1 from equation 2. It will make coefficient of x1 0 in equation 2. So if we write as a complete operation on a matrix, you will see that row 1 is no change, row 2 is row 1 plus row 2, and row 3 is again no change. So you need to find out what matrix you should find out, what matrix should be there, and from which side it should be multiplied to this particular matrix, to this matrix, so that you can get this one. So that you can get this one. So that you want, that you need. So look at the previous lecture or the previous section and try to find out what matrix could be there. I perfectly believe that it is easy. Okay, so once we do that, we are able to achieve this matrix. So you can see that in this particular matrix, this 0 has appeared and corresponding changes are there in the rest of the row. The other two rows are exactly same as previous. Now in the next iteration, what I want to remove this 2 from equation 3 and make it 0. So what we can do, we can replace equation 3 by equation 3 minus 2 times equation 1, right? So okay, again you have to make an expanded operation as this one, so as to get a matrix, and you again need to find out whether it should be multiplied in the right hand side or the left hand side. So after doing that, you can get this one. Multiplying the matrix from so that the row operation happens and the row operation, since both of them are equivalent, it doesn't matter how actually you do it. You do it by matrix multiplication or you do it by combining the two equations. It actually doesn't matter. What matters is that you know that both of them are equivalent. Okay, so let's move to let's try to see what we will get. So we get this particular thing, this equation, this matrix we get. Now from this particular matrix, we want to remove 5 from equation 3, which is directly below equation 2's 4. Okay, which can be done by replacing the equation 3 by equation 3 minus 5 by 4 times equation 2. Why we have not used equation 1? It's simple, because if we have used equation 1, then this 0 this 0 would have been changed to some non-zero quantity which we don't want. So we took instead equation 2, which has already a 0 in as a coefficient of x1. So it will not change the coefficient of x1 in the equation 3, definitely. Now with the help of this particular equation, equation 2, we are going to remove this 5. Okay, so once we do that, we will achieve this matrix. Now let us just try to understand means what in a general perspective we have done with the Gauss elimination. First of all, we started with the equation 1 and we tried to find out what is the first element, first non-zero element. This non-zero element, with the help of this non-zero element, non-zero coefficient of a particular variable, we try to make the coefficient of that particular variable in other equations 0 by suitably scaling that equation, the equation number 1, and then adding it to the other equations so that we can create zeros below it, right? Now same thing we did. Now again we come to the equation 2, find out the first non-zero element. This first non-zero element is again used to make zeros below it in the same column. It is not creating anywhere else, it is just creating in the column below, in that particular column and below it. So for that purpose, you can see here 4 is trying to make 0 just below it, that is 5. In place of 5, we want to make 0. So that's the crux of this process. Once we are done with that, we can actually easily go for the back substitution and try to solve it. So okay, I'm trying to define pivot. Pivot is the leading coefficient of a row. So it's a leading coefficient of the row, leading coefficient of the row, which is a non-zero number, right, from the left, and it is called pivot. So in this particular matrix, 1 is a pivot, 4 is a pivot, and again this one is also a pivot, which is a non-zero quantity coming from the left, from the first non-zero quantity from the left, right? So this is called pivot. And then you do a back substitution, and once you complete the back substitution, you get the solution. As a homework exercise, what you can do, you can try to generate a Python or a MATLAB program so as to solve a unique system of linear equations with a unique solution, and you will find that it's okay that you can actually do it. So in the next video, I'm going to talk about row echelon form and the importance of row echelon form in actually handling all the 3 cases. Thank you.